Hello student. Today I am going to start about my second lecture of control system 2 through video lecturing. So um, last class what we have understood that the concept of equilibrium points and linearization. I hope that all of you have understood that how you will find the equilibrium points for a linear system as well as for the nonlinear system. Especially for the nonlinear system, we have observed that the multiple equilibrium point can exist. In contrast to that, for a linear system, only single equilibrium point, that is origin. And for a nonlinear system, if multiple equilibrium point exist, then we can linearize the nonlinear system about its equilibrium point. And how we can linearize that already we have discussed. Now as I told you that to discuss about the equilibrium point and the linearization technique is that our aim is to discuss about the stability of a given system which is represented in state space. Okay, and also we will learn about the especially the stability of the nonlinear system also. Very uh, basic thing we will learn. Okay, not in very deep but in a basic what are the basic things about the stability of a nonlinear system that we will study. Okay, so with that aim today's class is very important, and I am continuing with the same slides what I have sent. Okay, now I'm going to the slide where we can start, that is uh, that is that as I told you that we are going to discuss about the stability which is defined for linear system and nonlinear system, which is represented in state space, and we will study the stability theorem given by Lyapunov. So he is a Russian mathematician and engineer who laid out the foundation of the stability theory, especially which we used to understand about the um, modern control theory. Okay, so his results was published in 1892 Russia, translated into French in 1907, reprinted by Princeton University in 1947, and American control engineering community shown their interest in 1960. Okay, so Lyapunov methods, in true sense we can say that it is a very general method to prove or disprove stability of a nonlinear system, and Lyapunov stability theory is the single most powerful method in stability analysis of nonlinear system. So if we able to analyze the stability of a nonlinear system, obviously we can analyze the stability of a linear system using Lyapunov method also. Okay, so today I'm not going to teach the Lyapunov theory, but before that some important thing we have to learn. So slowly we will learn what is Lyapunov theory. Okay, so now we are going to understand about the notion of stability for dynamical system. Okay, so already one notion we have studied in classical control theory, that is called Bigot stability, bounded input bounded output. Okay, so here we will learn clearly two distinct notion of stability, that is called internal stability, which is also known as Lyapunov stability. So this is a property of the state representation and does not concern inputs or outputs, just the zero input response. Okay, means here only we will define the stability in terms of states. So we are not interested about the input output behavior of the system. So that's why you can assume that for the to judge the internal stability we will assume that input is zero. Okay, so roughly you can say that if the state is close to an equilibrium, it stays close, means that the system not the system, it means that this is a stable equilibrium point. As I said you that there will be a chance of multiple equilibrium in case of nonlinear system, so no longer we will call it system is stable. Instead of that we will use to tell that equilibrium point is stable. So if a state is close to an equilibrium point, even if the perturbation is given, it stays close to that equilibrium point, and then we say that that equilibrium point is stable equilibrium point. And what is the definition of external stability, which is known as Bibo stability also? It is bounded input, bounded output stability. So from the name, it has been clear that we are actually considering only the input output behavior of the system. There will be no consideration of states. So that's why it is a property of the input output response. So it is a zero state response. Roughly, if the input is small, the output also will be small. Means for a bounded input, the output also will be bounded. Okay. Now we will discuss about certain definition which is used for a LTI system expressed in state space representation. So here the system is represented by x dot equal to ax, xt belongs to Rn, n number of components are there, and the initial conditions are indicated by x naught. Okay, so this system is called internally stable, because Bibo stability already we have discussed, and also again we will discuss to find out the relation between the internal stability and with the Bibo stability. But time being, we are giving the definition of the internal stability. So this system x dot equal to ax is called internally stable if the states, that is xt t greater than 0, remains bounded for any bounded initial state x0, for any bounded initial state x0. Okay, and the system is called asymptotically internally stable if it is internally stable and the state decays to 0, means norm of xt, sorry, here x of t will be inside the norm, x of t tends to 0 as t tends to infinity. Okay, this is the definition of the asymptotic stability. So asymptotic internal stability, or in short AIS, when it is internally stable and moreover that all the state decays to 0, mathematically it means that norm of xt tends to 0 as t tends to infinity. And what is the definition of exponential stability? Now the system is called exponentially stable if there exists alpha greater than 0 and m greater than 0, these two positive constants, such that for all t greater than 0, norm of xt must be less than equal to m into e to the power alpha t norm of x0. So here you see that all the definition involves xt. Okay, means the solution of this set of differential equation x dot equal to ax. Okay, so every solution of x dot equal to ax is bounded by decaying exponential in t defined by m alpha and norm of x0. That is the definition of exponential stability. Now our concern will be that what are the requirements to become a system asymptotically stable? Okay, asymptotically internally stable. Okay, so now to do that one, the next analysis we are doing, that is requirement. What is the requirement of asymptotic stability? So what is the requirement of what is the definition of asymptotic stability? Asymptotic stability definition is that norm of xt tends to 0 as t tends to infinity. We have to establish that one. So that's why let us look at this requirement carefully. We solve the system x dot equal to ax explicitly, and we know that what is the solution. Solution is xt equal to e to the power at x0. So now if this is the solution, then if norm of xt tends to 0, it is equivalent to say that norm of e to the power at x of 0 or x naught must be going to 0 as t tends to infinity. You see, x0 will be given and it is constant. So norm of e to the power at must be going to be 0 as t tends to infinity. So what are the elements of, or what are the entries of e to the power at? Okay, so in the last class, not last class, means before mid-sem, you can remember that several examples we have taken to understand what are the possibilities of entries of e to the power 80 for different cases. Okay, means if the roots are repetitive, if the roots are complex, if the roots are real, then what will be the entries of e to the power 80. So in general, from that fact, we can say that the each coordinate xj of t, because xt is e to the power 80 and xt having n number of component. Okay, so n number of component means x1 x2 xn is the linear combination of following n functions, because depending on the entries of e to the power 80. So what are they? Now the functions may be t to the power l e to the power lambda t, okay, where lambda runs through the distinct real eigenvalues of a, and l is an integer. It depends on the multiplicity of lambda. Means if there is no multiplicity in the lambda, then you will find that e to the power 80, the entries of e to the power 80 will be simply e to the power lambda t. Okay, if the roots are real and distinct, and it may be the linear combination of t to the power l e to the power 80 cos of bt, t to the power l e to the power 80 sine of bt, where a plus jb runs through the complex eigenvalues of a having b greater than 0, and l is an integer with which is varying between 0 and multiplicity of a plus jb. Means what I want to mean that the e to the power 80 entries of e to the power 80 depends on the eigenvalues of a. Okay, so it may be t to the power l e to the power lambda t, or e to the power it will be t to the power l e to the power 80 cos of bt, or t to the power l e to the power 80 sine of bt. Okay, means suppose if, for example, if there is the roots are on the imaginary axis, then you will find that it will be simply the terms, you will find that it will be simply cos of bt sine of bt. Already this examples we have solved. So now, after knowing that these are the possibilities may exist in the entries of e to the power 80, then how we can conclude about the asymptotic stability of a system. Okay, so the system x dot equal to ax is asymptotically stable if and only if real part of lambda I is strictly less than 0 for all I 1 to n. Okay, means what is the meaning of that? That this e to the power 80 norm of e to the power 80 going to be 0 only when this lambda is negative. Okay, lambda is negative. So that's why, or if it is having, if it is a complex root, then this a must be negative. Okay, so that's why real part of lambda I, that is lambda is basically here representing the eigenvalues. So real part of eigenvalues must be less than 0 for all I 1 to n. Okay, so the system is asymptotically stable or exponentially stable if and only if all the eigenvalues of a are in the open left half of S plane. Alternatively, we can say that one. So you can remember this one is very important to understand, that what is the requirement of asymptotic stability, that the all the eigenvalues of the system should have negative real part. Okay, strictly all the eigenvalues, that you remember. Okay, now we will try to understand whatever we have discussed here. We will try to understand with an example. Suppose we have a system x dot equal to ax, where a matrix is a Jordan matrix. You can see that one. So here, from here it is clear that we have poles or the eigenvalues, triple eigenvalues at a is equal to -2. Okay, so we have to establish that whether this system is asymptotically stable or not. So if it is given to you, then we have to see what are the entries of e to the power 80, because requirement is that norm of xt must be tends to 0 as t tends to infinity. Okay, so now if we calculate the e to the power 80, we are finding that it is either e to the power minus 2t or t into e to the power minus 2t has come. Because why t into e to the power minus 2t has come? Because here the multiplicity of the pole is means minus 2 the pole particularly that is minus 2 3 times it is repeated. Okay, repeated poles are there. Okay, so multiplicity is 1. Multiplicity is 1, that's why t to the power l become 1. Okay, now if I want to find out the xt after knowing the e to the power at, xt we can write like this: e to the power at into x of 0. And now you see here, though it is given 1 1 1, but you can see that the analysis true for any initial condition. So that's why I have taken x01, x02, x03, the any real values. Okay, so x1t you are finding that it will be x01 e to the power minus 2t, x2t is the linear combination of these two terms, x3t is x03 e to the power minus 2t. And from this expression it is very much clear that at t tends to infinity all these components are going to be 0, because you see that the exponential have negative sign, that is minus 2. Okay, so from here it is very much clear that system is asymptotically internally stable, because for any initial condition we can say that norm of xt is going to be 0 as t tends to infinity. If all the individual components are going to be 0 at t tends to infinity, then definitely norm of xt is going to be 0 as t tends to infinity. So in this way we can establish the asymptotics, or we can test the asymptotic stability of a system. Now most important thing we have to understand today, that is what is the relation between the asymptotic stability and the external stability. Okay, so when we are talking about the external stability or input output stability, we will assume that 0 initial condition. Okay, and the definition of the Bibo stability is that a system is externally stable or Bibo stable if any bounded input ut bounded, that's why it will be less than equal to m1. Okay, some finite value produces a bounded output yt which is less than equal to m2, another bounded value, another finite value m2. Okay, and from the previous analysis we have understood that a system is Bibo stable if and only if the impulse response of the system is absolutely summable, means 0 to infinity mod of ht dt is less than equal to m is a finite value, that's why it is always less than, strictly less than infinity. Okay, so this is the definition of Bibo stability already. Now we want that what is the relation between Bibo stability and asymptotic stability. Now one fact I am going to tell, or one claim I am going to do, that is asymptotic stability implies Bibo stability. Means what is the meaning of that? The asymptotic stability is the stronger notion than the Bibo stability. Means if we able to establish that a system is asymptotic stable, then definitely the system will be Bibo stable. How? Now here the proof is very simple, you can understand very easily. You see, we know that the impulse response of a system is calculated by c into e to the power at into b. In my class I have discussed that the impulse response of a system ht will be c into e to the power at into b. So what is the requirement of Bibo stability? The impulse response must be summable. So now you see what will be the impulse response, and that will depends on the entries of e to the power at, and they will be the linear combination of t to the power l e to the power lambda t, t to the power l e to the power at cos bt, t to the power l e to the power at sin bt. So now if the system is asymptotically stable, just now we have understood that this this lambda and a must be less than 0. So hence each of these quantities are absolutely summable. So ht will also be absolutely summable. So in general we can say that the converse is not true. Means if a system is Bibo stable, then we cannot say that system is asymptotically stable. That we are going to understand certain example now I am going to give, but this thing has to be clear that asymptotic stability implies Bibo stability, means asymptotic stability is the stronger notion than the Bibo notion of stability, that is called Bibo stability. Okay, so now what is the fact it is telling? That Bibo stability is equivalent to the asymptotic stability if the realization is minimal, means if there is no actually no pole zero cancellation. Okay, now you see the next slide is introduction to Lyapunov stability, that today I am not going to discuss. Only I am going to discuss about the relation between Bibo stability and asymptotic stability with certain example. Here as a note I have written that in general the converse is not true, that is Bibo stability does not imply the asymptotic stability. That we are going to understand certain example. Okay, so suppose the example is something like this, and it is a very interesting thing, and later on also we are going to understand in a great details with some other angle. Okay, so now you see this is the system x dot equal to ax plus bu, y equal to cx, where a is in a special form, you can see that is in a diagonal form. Okay, so what the diagonal elements? -1, -3 and -6, and we know that these are the eigenvalues of the system. Okay, and B matrix is given like this and C matrix is given like this. Okay, so clearly this system is asymptotically internally stable because all the eigenvalues have negative real parts. Okay, so now what will be the transfer function for the system? Now we can calculate by C into Si minus A inverse into B, and we are finding that the transfer function is 1 by s plus 1, s plus 3, s plus 6, means the system is Bibo stable, because we understand that Bibo stable means all the poles of the system should have negative real part. Okay, so here what are the poles? Now a is equal to -1, a is equal to -3, a is equal to -6. So Bibo stable, note that in this case all the modes have shown up in the transfer function. We will try to understand what is the meaning of all the modes shown up in the transfer function, and probably from this discussion we will have an idea what is the difference between eigenvalues and the poles of a system. You see here for this system, the system what is represented for this system, the eigenvalues and the poles are same. Okay, eigenvalues are -1, -3, -6, and the poles are -1, -3, -6. Okay, now we will modify the system, the same system slightly, and this is our example 2, where A is -1 plus 3 and -6, and B matrix has been changed. You see the second element is become 0 and C is as it is, like 1, 1, 1. Now if I will ask you by observing the A matrix, that can you comment about the asymptotic stability of the system? You will say that the system is not asymptotically stable because one of the eigenvalue is positive, that is +3. Okay, and if you able to solve this using the formula, you know that for that formula is showing that you see x2t is equal to e to the power 3 into t minus t0 x20. So for any initial condition this mode is unstable because this e to the power is going to blow. But now you see the input part, if you see input part is 0 because due to this second element is 0. So nothing you can guess what is the need to write this expression, nothing you can guess basically by observing input output relationship, because this second element is 0, so that's why this part will be vanished. Only you can understand about the internal, so that's why it is called internal stability, because you will find that due to the existence of this +3, okay, this mode for any initial condition x20, this mode is going to increase exponentially. instead of decrease. Okay, so that will be understand if you will find out the transfer function for this system. If you find the transfer function in the same way, G is equal to C into Si minus A inverse into B, you will find that the particular mode, that is the unstable mode, is not visible in the transfer function. The transfer function is s plus 4 by s plus 1 into s plus 3. So here what are the so if only this transfer function is shown to you and it has been asked that can you comment about the Bibo stability of the system, you will certainly say that the system is Bibo stable because the poles are at s plus 1, is equal to minus 1 and is equal to minus 6. So system is Bibo stable, but it is not internally stable because the particular mode is not visible due to the particular representation of the system. Okay, because this element is 0. So that's why you cannot see. So that's why the eigenvalues for this system is minus 1, plus 3, minus 6, but the poles for this system is equal to minus 1 and is equal to minus 6. So that's why the system may be Bibo stable, but it doesn't guarantee that system will be asymptotically stable. Okay, so the mode corresponding to lambda equal to 3 is said to be uncontrollable from U, and thus it does not appear in the transfer function. So here a new term you are going to is introduced, that is called uncontrollable, because you see this U term corresponding to means corresponding U turn to this particular mode is 0. So that's why you do not have control on this particular mode. So that's why it is called uncontrollable mode. Later on we will discuss these things about in great details. Okay, now we are considering another example where A matrix is taken minus 1, plus 3, minus 6, B is as it is, but C matrix here the second element we have taken 0. And similar way you can say that, you see, if you see because this is the advantage of the presentation of any system in diagonal representation, because here you can see all the eigenvalues very clearly. You see it is minus 1, plus 3, minus 6. So similarly we can say that it is not asymptotically stable. And if you find out the transfer function for this system, you will be surprised that the transfer function is s plus 4 by s plus 1 into s plus 6. Again the system is Bibo stable but not internally stable, and here the mode according to lambda equal to 3 is said to be unobservable from Y, because this particular element is 0. So actually we cannot, so this C is involved with the output equation. So that's why this is this particular mode is unobservable from the output Y. Okay, which we have seen that this particular mode is uncontrollable from the input. So that's why these two cases we have observed that this example 2 and example 3 we have observed that system is Bibo stable because the poles are at minus 1 and minus 6, but it is not asymptotically stable because all the eigenvalues do not have negative sign. Okay, so from here many things we have learned. So I will conclude here for today that we have learned the definition of the internal stability and the external stability. Then we have learned in internal stability 3 notions of stabilities are there. That is that means that internally stable. Then we have learned about the asymptotic stability. Then we have learned about the exponential stability. Then we have learned what is the requirement of asymptotic stability. The requirement of the asymptotic stability is that all the eigenvalues must have negative real part. And then we have understood that if a system is asymptotically stable, then system must be Bibo stable, but the converse is not true. Means if the system is Bibo stable, we cannot say that system is asymptotically stable. So in the next class we will start about the notion of Lyapunov stability, and the theorem of Lyapunov stability. Okay, thank you.